Now that we have all these properties, let's go ahead and put this into context with a word problem. So, if you walk in a normal way, your maximum speed, v, in meters per second, is limited by the length of your legs, r. Now, according to the formula, v equals the square root of g times r, where the constant g is approximately 10 meters per second squared. So, what we're working with here is that if we're using this constant that g is 10 meters per second squared, and the meters per second squared is units, it looks something like that. So we're not going to be squaring the 10. All this does is it tells us that our formula that we're using here, if that's our value for g, we're using a square root of 10 times r. Okay, so a typical adult has legs about 0.9 meters long, so how fast can they walk? So we're going to go v equals square root of 10 times 0.9. And with these, well, actually that's not too bad. This is a square root of 9, which is 3. So that would be a speed of 3 meters per second. A typical 4-year-old has legs 0.5 meters long. How fast can they walk? So v equals the square root of 10 times 0.5, which is the square root of 5. And let's go ahead for a word problem, put this in our calculator to get a decimal out. And that's going to be 2.24 meters per second. So graph maximum walking speed as a function of leg length. And what I'm going to do is I'm going to go ahead and do this in Desmos so that we can just look at a nice picture of it. So I'm going to grab our Desmos graphing calculator and we're going to graph the square root of 10 times x. So square root. What I did there, so you can grab the square root symbol from the keyboard down here at the very bottom. Sorry, it's a little off my screen. Or what I did here is I just started typing in SQRT for square root, and it automatically changes it to the symbol. So either way. And then we're going to go 10 times x. So what we should be seeing here, if we think about our graph transformations, is we're seeing our radical function square root of x, but what we have here is a horizontal compression by 1/10. So everything's getting squished towards the y-axis. So if we think about our regular function of just square root of x and do a comparison, it's a lot flatter because it's kind of increasing more slowly, but because of this compression, it's all much closer to the y-axis. So just as a comparison and kind of a visualization of what that 10 is doing, it's causing a horizontal compression. Okay, race walkers can walk as fast as 4 meters per second by rotating their hips so that the effective length of their legs is increased. What is that effective length? So what we have here is a velocity of 4 is given to us, and we're going to solve for it. So 4 equals 10 times r. We're going to square both sides, divide by 10 for 1.6 meters. So as a comparison, typical adult has legs of about 0.9 meters long, and how they're working it, they have an effective length of their legs of 1.6 meters. Pretty cool. Okay, on the moon, the value of g changes to 1.6 meters per second squared. So our formula is going to change. V equals square root of 1.6 times r instead of 10 times r. And we're going to go back to our typical adult with 0.9 meters long. So we're going to go v equals square root of 1.6 times 0.9. And let's go ahead and put that into the calculator. So a square root of 1.6 times 0.9 for 1.2 meters per second. So let's see. Gosh, that's half the speed of a 4-year-old walking. So If you imagine a toddler walking on the moon, you could go about half that speed based on this formula here. So just some scenarios with square roots coming through in context of an application.